based on the premise that the metal ion and the ligands can be treated as point charges, and the spatial arrangement of these point charges will affect the energies of the d orbitals for the central metal atom. These are the orbitals that ligands donate electron density into, so these are the chief concern for the model. And this model, although incomplete, just like VSEPR theory or valence bond theory, does wonderfully explain things like the colors, magnetic behavior, and structures that can be observed with coordination compounds. The first thing we must understand is that ligands all have excess electron density that they are donating to the metal ion, and this electron density will repel existing electron density on the metal ion. Due to this repulsion, the energy of certain d orbitals will be increased, and not in an equal manner. To understand why, let's look at this octahedral complex, a very common geometry for coordination compounds. The central metal atom has valence electrons in these d orbitals, which when unhybridized look like this. We must note that two of the d orbitals, the dx squared minus y squared and the dz squared orbitals, have lobes that extend on the x, y, and z axes, meaning that electron density is sitting on these axes, whereas the other three orbitals have lobes that sit in between the axes. Looking at the octahedral complex, the bonds to the ligands also sit on these axes, which means that in order for ligands to approach the metal atom, their point charges must repel the electron density in these two orbitals. For this reason, whereas for an isolated metal atom, the d orbitals all have the same energy, in an octahedral complex, these two orbitals we mentioned have a higher energy as they point in the direction of ligands, and we refer to them as the Eg orbitals, while the other three are the T2G orbitals, which point in between ligands. The difference in energy between these two sets of orbitals is called the crystal field splitting energy. The magnitude of this energy gap will depend on whether the orbitals involved are 3d, 4d, or 5d orbitals, as well as the identity of the ligands themselves, with the impact following this trend here, called the spectrochemical series. On the left we have weak field ligands, and on the right, strong field ligands. Let's put this into context. For an isolated metal atom, once again, all the orbitals are of equal energy. If the metal is participating in a complex with weak field ligands, the difference in energy is small and not enough to overcome the pairing energy, or the repulsion generated by doubling up electrons in an orbital. In such a case, they will spread out evenly, putting unpaired electrons in the Eg orbitals before the T2G orbitals are completely full. These are called high-spin complexes. But if in a complex with strong field ligands, the difference in energy is very great. In such a case, the system will be at a lower energy by simply doubling up electrons in the lower energy T2G orbitals. These are called low-spin complexes. Crystal field theory works for geometries other than octahedral as well, like tetrahedral, which tend to be high spin, but the ligands orient themselves differently, so they interact with the orbitals differently, and we get different energy diagrams. Specifically, with this geometry, ligands more closely approach the d orbitals between the axes rather than the orbitals on the axes, so the higher energy orbitals are precisely the opposite ones as in the case of octahedral geometry. Also, the ligands don't approach the orbitals as directly, so the energy splitting will be of a lesser magnitude. We can do something similar for square planar geometry as well. So to reiterate, the strength of the ligands surrounding the metal atom, along with other factors like oxidation state and coordination number, will determine the magnitude of the crystal field splitting energy, or the difference in energy between the T2G orbitals and the Eg orbitals. This in turn will determine the electron configuration and thus other characteristics of the complex, such as paramagnetism versus diamagnetism, and the corroboration of the predicted magnetic behaviors of different coordination compounds is very strong evidence in favor of crystal field theory. More evidence comes from examining the colors of visible light emitted by certain compounds. We know that atoms absorb light of certain frequencies depending on the element they belong to, which results in an electron going to an excited state. And when an electron goes from an